Sorry, I'm recording. Okay. Isaac, sorry, we just got started. We're just kind of remembering how we talk about a derivative of a curve at a point. So these are some notations here. We could also say if y equals f of x, we could also call this, we could say y prime or dy dx, right? Or derivative of y with respect to x. So here's common notations here. So anyway, but then we get a second derivative. What's a second derivative? Second derivative is just the derivative of a derivative, right? So for the second derivative of a function, that's the instantaneous rate of change of a curve, the derivative curve at a point, right? It's the slope of the tangent line of the derivative curve. So that would be the slope of the tangent line evaluated at f prime at x. But some second things here. Anyway, there's f double prime of x, so we can put two tick marks up there, right? F double prime at x. We could also say the second derivative of f with respect to x. But the way we do this, remember, dx is a variable, so dx squared is just dx dx on the bottom. So the second derivative of f with respect to x, I had to say it with capital, is d squared second derivative of f with respect to x. So these are some notations here. Of course, we could have y double prime, stuff like that. So anyway, but it's the derivative of the derivative. So the second derivative really could also be the derivative with respect to x of f prime at x, right? That's really what it is. So we could call it df prime dx, the derivative of f prime with respect to x, right? Things like that. So we've got some different notations there. Of course, we could have, so we got first derivative f prime at x, then we got second derivative, we can say f double prime at x, third derivative f triple prime at x, that's the third derivative, right? And then we got the fourth derivative, but obviously we start getting into tick marks that are hard to read. So what we do is we use Roman numerals. So that's like Roman numerals, like Roman numeral 1, 2, 3, and except they're slanted. Then what we do is we're going to put, if we get 4 bigger, we're going to put, like in this case, IV, lowercase, Roman numerals, fourth derivative of f, fifth derivative of f, evaluated at x, things of that nature. So we're going to use little Roman numerals there, so we can keep going, right? Real simple thing. Let's just look at an example, which I think is in my notes. But if I have f of x equals x to the 10th power, we know what that looks like, right? What's the shape of that curve? What curve does it look like? What base graph does it look like? X squared. It looks like a parabola, right? It's not technically a parabola. It looks like a parabola. Right? It's a U shape, right? And if I want f prime at x, so I'm going to go red. If I go f prime at x, at any point, it's the slope of the tangent line, right? So if x is greater than 0, what do you know about the slope of the tangent line? Is it positive or negative? It's positive. And the farther right x is, does it get steeper, like more positive or less positive? More positive. If you get closer to 0, does it get more positive or less positive? Less positive. So less positive to more positive looks like that, doesn't it? That's f prime. But look on the left side, what kind of slope of the tangent line? Can you see red? Okay. Negative, right? Negative slope. What happens as you get closer to 0? Is it more or less negative? Less negative. Less negative, right? So it's as you get away from 0 toward negative infinity, it gets steeper and steeper negative, like more negative. So basically it's less negative to more negative, and then of course at 0, it's a horizontal tangent line, right? It sits right on the x-axis there, correct? So anyway, what's that look? It kind of looks like x cubed, right? If you take the derivative of x to the 10th power using the power rule, which is the easy version in section 2.4, theorem, what is the derivative? 9x to the 10x to the 9th, right? 10x to the 9th power. Well, what's that look like? It looks like x to the 9th, which looks like x cubed, and then times 10. Sorry, that's terrible. 10x to the 9th power. All right, so what if I want let's do it again. I'm going to use a different color, use green. What happens here? I'm slightly positive, more positive, even more positive. So f double prime at x, when I go to the right of 0, gets more and more positive. It looks like that, right? What about when I go left? It's positive, more positive as you go left of 0. So it's more and more positive. So it ends up looking like this. It's a bowl shape again. So it's kind of a parabola, right? Not very well driven. It's not drawn to scale, but it's a parabola. If you take the derivative of 10x to the 9th power using the two theorems that we have, derivative of constant times function is the constant 10 times what's the derivative of x to the derivative of x to the 9th is 9x to the 8th, and then times 10, so 90x to the 8th power, right? Kind of hard to see the light green on here. I don't know why they don't use dark green. Anyway, what's the shape of that look like? It still looks like a parabola, right? So we can keep going down. Like I can do the third derivative. I'm not going to draw it. I'm not going to, but slope of the tangent line, once again, more and more and more positive as you get right at 0, and less and less negative coming in from the left. But anyway, f triple prime is going to be what? 8 times 9 is 7 x to the 7th power, right? Now we can keep going here on this, and anyway, eventually it flattens out. So I started out too high here, but let's do a little easier one. Let's start out with y equals x to the 4th. Well, same deal. It looks like this, right? Y prime equal 4x cubed, which actually what's going to happen is it'll flatten out. What's y double prime? 12x squared. But what really happens is we're widening out here, just so you know. And y triple prime, 24x. Well, what's that look like? It's a line with a slope of 24, right? So what's y to the 4th of x? Fourth derivative of y with respect to x. 24, right? What's that line look like? All lines are straight. Quit saying straight line. It wasn't just you. Other people said that too. It's a horizontal line, right? And then, of course, what's the slope on the line? 0, that's the x-axis, correct? In this case, for this one, yeah. So, but what happens is, even though, you know, we kind of, the back one looked like it kept going back and forth between something that looked like x squared and something that looked like x cubed, right? But what was happening, it was widening out, and actually it gets wider as you're going, and then ends up being an actual line at some point. And then horizontal line, of course, anyway, this, and then the x-axis here. So anyway, so we have those. But then there was one in there, second derivative. Is there an odd for second derivative or third derivative? It's like the even determinant today or tomorrow. $43, $41. What's that? And the second derivative of y with respect to x. Okay, so once again, notation, it's dx squared. D squared y over dx squared. is the second derivative notation, right? You could also say y double prime. I don't care. It's y double prime, but you need to be able to, I don't care what you write down on your paper, but you need to be able to raise both of those symbolizations for it. Anyway, so what is y prime? Well, what do we got to use here? Now, what do we got here? What kind of rule do we got to use? We have certain theorems that I threw at you in a flurry. What type of function is this? Yeah, quotient, right? So polynomial divided by a polynomial. It's a rational function, so I got to use the quotient rule. What's the quotient rule say? It says the bottom one times the derivative of the top one. What's the derivative of the top one? It's 4x cubed, because the derivative of 1 is 0, right? Minus the top one, which is x to the 4th plus 1, times the derivative of 1. What's the derivative of x squared? 2x using the power rule, right? All over the bottom 1 squared. So x squared squared is x to the 4th. Okay, now in this case, we could leave it like this if we want and then take the derivative again, but that gets kind of awkward. So wouldn't it be a lot easier to simplify first? Right, so I'm going to simplify first. So I'm going to multiply that out on top. So that's equivalent to 4x to what power? Same base. To the 5th power. If you're not sure, you can write that's x. This one's x times x. This one's x times x times x. How many x's do you have? Multiplied together, 5, right? So same base, add exponents. Anyway, so it's 4x to the 5th, and then minus the quantity 2x to the 5th plus 2x, right? All over x to the 4th. Now in this case, I can add the opposite. So if I add the opposite, I got that, and then that's equivalent to 2x to the 5th minus 2x all over x to the 4th, right? You agree? How's that simplified? No, if in doubt, factor it out. What could I factor out of the top? I could factor a 2 out. It doesn't really help anything, but what else could I factor out? I could factor out a 2x, or I'm going to factor out an x, because that'll cancel on the bottom. So it's x times the quantity 2x to the 4th minus 2. And then what happens is I'm able to cancel that x with one of these, right? So you're going to remember 2x to the 4th minus 2 all x cubed. Two x to the 4th minus 2 all over x cubed. Is that right? We're going to take the second derivative, would be the bot, and once again, it's a quotient, so we're going to use a quotient rule, right? Everybody agree? So it's bottom times the derivative of the top. What's the derivative of the top one? 8x cubed minus the top, 2x squared minus 4, minus 2, I mean, times the derivative of the bottom, which is 3x squared, right? All over the bottom 1 squared. What's x cubed quantity squared? What's x cubed quantity squared? X to what power? X to the 6th. That's the amen rule. X to the m to the n. Sorry, a to the m to the n. That's the amen rule. Amen. A to the m times n. Again, amen. Amen. All right. So get on that, and then of course, what can I do here? Multiply this through here, right? Let's try and simplify this, and then multiply these two together. So I get 8x to what power? Third times 8x to, or x cubed times 8x cubed is 8x to 6. Same base, add exponents. And then minus the quantity would be 6x to the 6th, and then minus 6x squared, right? All over x to the 6th. You sure this is the one S? I'm going to add the opposite. And what do I got? So I got 2x to the 6th and plus 6x squared over x to the 6th, right? And then I could factor out an x squared and rewrite that. If I do that, I'm going to put my answer over here in black. So it's 2x to the 4th plus 6 all over x to the 4th. If you factor out an x squared on the top, right? So I could write that as x squared times 2x to the 4 plus 6 all over x to the 6. So that cancels with 2 of those, right? Everybody agree? Okay, now I'm going to show you a different way. Now, if I divided each part, that's actually, what's this equivalent to? I could divide each term by x to the 4th, right? So I'd get 2 plus 6 over x to the 4th. Does everybody agree? So where the x to the 4th is only under the 6th, you divide each part. That's just rule of fractions. So let me go back to the original one. And what was the original problem again? Divide by x squared. So I could actually rewrite this by taking x squared. You know, if I have a plus b all over c, that's equivalent to a over c plus c, right? Do you agree? Principal law of fractions. So anyway, so this is x to the 4th over x squared, which is x squared, plus 1 over x squared, which is, I could write that as x to the minus 2nd power. So isn't it equivalent to x squared plus x to the minus 2nd power? If I take the derivative of this, what's the derivative of x squared? 2x, so derivative of the sum is the sum of derivative, and then plus, what's the derivative of x to the minus 2nd? Minus 2x to the minus 3 power. So remember, you take that exponent, you drop it down in front, and then you reduce it by 1, which means it goes left by 1. So y prime actually equals 2x minus 2x to the minus 3rd. Do you agree? Can I take the derivative of that with respect to x? What's y double prime equal? What's the derivative of 2x? 2. And then the derivative of the second part. So I can take that, I'm going to switch colors again, take that minus 3, drop it down in front, attach by multiplication. Minus 2 times minus 3 is plus 6, x to the minus 4th. Right? Well, what's that equivalent to if I rewrite this? It's 2 plus 6 over to the 4th. Which did you prefer? Second way or first way? Second way is a lot easier because you're just using the power rule basically, right? But you got to rewrite it. So it's all equivalent. Is that what the back of the book had for the second derivative? Yeah, Isaac's not here, so nobody's allowed to ask me questions that are wrong in the back of the book anymore. That's what they got, then the book is correct, because I know I am. Sister! Yeah! Boom! Eat that for lunch. Okay, anyway. What else do you want to know? Anything in 2.4? 2.5 and 2.6 is where life gets a little challenging. We have word problems. We have stuff like that. No other question? Any other questions in 2.4? Last chance. I have no idea what's in 2.5 or 2.6. I'm not very prepared. I had appointments this morning. We got a new president. People want to know what to do with their investments. Buy, baby, buy. Invest in America. Anyway. 2.4, no other questions on 2.4? It says support graphically, so what do? By the way, if it says support your app graphically in numerical, in the same, if it says in a window, it means on a graphing calculator, so we don't have to do that. You can do that. As you know, it's not very hard to graph some of that stuff. Could I graph that one? Oh, well, let's graph number 41. What was that? What was our answer? We had y double prime equals 6 plus, what was it? 6 over x to the fourth plus 2. Okay, so it's basically this one. Well, what's 1 over x to the fourth look like? Looks like that, multiplied times 6, so it squeezed a little tighter. I don't have a scale on there yet, but it looks like that. That part looks like that, right? And then what am I doing? Up 2. What type of shift is that? An upshift, right? Look like that. Do they have a graph in the back of the book? Funky Brewsters, of course they didn't. Anyway, it looks like this. If I wanted to know exactly where it crosses, the never crosses the y-axis, right? But if I want to know exactly where it crosses the x-axis, that's where your height is 0, right? So I could set that equal to 0. So I get 6 over x to the fourth equals minus 2. That doesn't make any sense. What? Do I have minus 6 over x to the fourth? Plus. Oh. You can't have a negative number. That doesn't. There's no real root. This is an irrational. It's because there's no. I don't know. It's a window. So jump out the window. Don't jump out the window unless it's by the ground like this one. Okay. What else? No other questions in all of 2-4. So that is formally due tomorrow. I would like it really quick. So section 2-5, rectilinear motion. This is where you really need to be watching my videos. You need to watch them anyway, but you absolutely need to watch them here because I can't recreate my videos in a short class session. Can't do it. It takes an hour to make 15 minutes. I can't do it. You got to watch it and then ask me when you have questions. But we can go through a little bit of it. We're going to talk about rectilinear motion. I'll just give you a little heads up to what that means. Anyway, so section 2-5, remember the double S like that? That's a section number. So section 2-5, we're going to skip. We are going to skip. We skipped 2-3, right? So we are going to skip something. The middle of page 146. You got page 146 in your book. Middle of page 146, the paragraph right above illustration 3. Until the top of page 149. So till right above illustration 6. So we're just going to skip that. Okay, because they're using like windows on a graphing calculator. We're going to stay away from that. All right, but let me try and give you some highlights. This is a physical application. So who is taking physics now? Who's going to take it next year? Everybody else. Okay. Hannah, taking physics. That's great. I could not get my daughters to take physics. I was so mad. You should take physics. Like, why would you take? It's math and science, and both are cool. Okay, so you should take physics. But anyway, worst grade I ever got in college was calc-based physics. Calc was the easy part of that class. I got one of the best grades in the class. It was a C+. Apparently, it was a weed out course for physics majors. Guess what? I didn't major in physics. It's off. All right, but anyway, so everybody has their own path, right? So if you like physics, I love physics in high school and non like calc-based physics, but calc-based physics is cool, but I had terrible teachers. So there are such things as terrible teachers. Glad to have one. Right? Because I'm a professor. I'm right either way. Doesn't matter. All right, I see you looking at me under that. Like snarling your lip like Elvis. All right, but anyway, let's just talk about physics here. What do we got? We got speed and acceleration, right? Now what we got in this section? Rectilinear motion. So what does rectilinear motion mean? Here's rectilinear motion. We have a line, which is a distance line. It's S of t. S usually represents, by the way, t for time, right? That time we're dealing in seconds or minutes or hours, but S of t is your position function. This is your position. By the way, typically when we draw a line like this, positive is to the right, negative is to the left. You agree? Positive to the right, negative to the left. all agree, right? So anyway, it's position at time t. So where do we start? What's your starting position? When time equals what? 0, because you can't go back in time, right? Can't go back in time, that's what I heard. Anyway, so S of 0, sometimes that's called sub-zero, means original position. So this is original position. It's where you start. Original position. Okay, anyway, so let's say 0 is here, so positive numbers to the right, but let's say I start at 8. Say I start at 8. So I'm not really above the line here, am I? So have you guys ever done etch and sketch? Like, we didn't have many games when I was a kid, but etch and sketch was one of them. You've seen Toy Story, right? So etch and sketch, you had 2 knobs. You go up or down, left or right, that's it. In this case, we're only going left or right. So I can go to the right, then left, then right, then left, and right, and left, and right, and left, and right, and left, and then go out to the right forever after that if I want. Right? Okay. So, but that's very hard to see. What I could do is I could draw a visual separation of what I'm doing on this. And of course, this is kind of like when you graphed inequalities in first year algebra, like x is greater than 3 was your solution, or greater than or equal to 3. And you just like went to the right, but it was on the x-axis, and then you had to scratch it in, then you went all the way through the paper, and then you're writing on my desk during lunch and leaving ketchup, and teachers getting pissed, right? So anyway, but I can draw it above, and I can go right for a while, then left and right forever. And I could just kind of do it like this. And maybe I stop and turn around at t equals 10 seconds. I might stop and turn around. No, not t equals 10. Let's say at 1 second I turn around, but I turn around at a position, and then I go left to a position in -4, and maybe that's at 3 seconds, at t equals 3 seconds. I'm here, and then I go to the right forever. So once again, really drawing this on my chart, this is your position. So if I start at 8, this is what it looks like. Everybody watch at the screen. Okay, so I'd go right to 10, I'd stop, turn around, go left to 4, then I'd stop, turn around, then go right forever, right? Very hard to see that, right? It's all etch and sketch there, so we could just go above. Isn't that stuff above really nice and pretty? That's how we're going to represent that. All right, so then what else do we need to know in physics? So S is your position function, all right? And then what's the instantaneous rate of change of position with respect to time? Velocity. So V is your velocity. By the way, velocity is 2 things, speed and distance, right? So velocity, V of t is your velocity at time t. That's speed and direction. It's also going to equal s prime at t, or if you prefer, it equals ds dt, instantaneous rate of change of position with respect to time. Okay, and then the absolute value of velocity is your speed, because we don't care which way you're going. Okay, and I talk about this in my things. And then we have acceleration. So a of t is your acceleration. Well, what's that? That's the instantaneous rate of change of your velocity with respect to time. So acceleration is dv dt, or if you prefer, v prime evaluated at t. But what could I also say what acceleration is in terms of s? What would acceleration be in terms of s? Velocity is the first derivative of s. Yeah, so this also equals s double prime. The second derivative of your position is acceleration. Acceleration is like your pull. Okay, it's like your pull. Okay, so then we have charts. So you're going to have to watch my videos. So what I want you to do, 2.5 and 2.6, if you notice on your homework sheet, or do together. Let me go back to my face if I can. I'll get back to that. Okay. Can you see me now? Oh, we can only see Hannah. That's right. You don't need to see me. But anyway, whoops, stop it. Anyway, so watch my videos. 2.5 and 2.6 are due to turn in together, right? Well, read or watch my videos and work some odds, especially in 2.5. But remember, 2.5 and 2.6 are together. So 2.5, do as much as you can in 2.5 for tomorrow, and watch the videos in 2.6. But watch and do some odds in 2.5. I want you to try these. I might have done them on video, but try a few of those odds. Okay. Anyway, we're going to come up with charts. But acceleration is like your pull. It's like a rubber band. So anybody that runs, if they're pulling you with the rubber band, you go faster, right? As you run. If they're pulling against you with the rubber band, you slow down, right? So the question is, are you moving in the same direction as the pull? And so there's some of that stuff in the chart. So watch my videos. 2.5 for sure. If you can get into 2.6 grade, do some odds. 2.4, I need that homework tomorrow for sure. Thank you. See you later.